So there's a certain probability that a ship is here. There's some higher probability that the ship is located here, laterally on the lake. Then the ship is supposed to turn here, and at this moment here, we have this obstacle, and if you project the obstacle onto this distribution curve that we have from here, we will have an area, and the fraction of this area compared to the whole area under the curve is the fraction that we use to figure out the number of candidates. If we have 1,000 ships going this way, and the fraction is 0.5, 50%, then we have 500 candidates that possibly could end up here if they do nothing. Similarly, in a crossing situation, the ships are distributed like this, and they come into this area, and there's a certain area here, a geometrical area, where they possibly can collide. And depending on the size of the ship, the length of the ship, and the speed of the ship, the probability of meeting is different. So if you have a higher speed ship, it will go faster through. If it's very short, it will have even lower probability than a longer ship. So that's the thinking behind it. You can see the complicated equations here, velocities of the ships, the distributions, and this effective diameter of this area, I think it is. We obtain the lateral distributions of the ships from AIS data, typically. You could also do it by other means, but today we have AIS, and most of the administrations are able to draw passage lines, and they can actually extract this information. So what we do in IREP is that we fit a mathematical distribution to some data we have derived from AIS and put that into the program. And the volume of traffic, how many ships do we have, we also get from AIS. What type of ships, that is, what lengths of ships we have, and how many of each category we get from AIS data. Now, when you then want to model something in IREP, you need to have a density map, a density plot. So again, from AIS data, we take a density plot, which then tells us something about where the real fairways are, where people are actually sailing. We can see that there's a high density here, and this is a traffic separation scheme in Malaysia, in Malacca Strait. We did, when we released the first IREP, we went to Kuala Lumpur and I did an analysis of the Malacca Strait. So you would then build a number of traffic legs, a network of legs, which would make up the whole model like this. And for each of these legs, you would then enter the distributions. And for each of the legs, you would also enter the number of ships on this leg and the categories of ships. Also, we model with polygons. We model the contours of the land and also any relevant shallow areas in the area of interest. This is how the editor looks. You can enter the distributions. You have the ability to mix a number of theoretical, any number basically, so you can arrive at any complex distribution that might be there. And then the number of ships, this is the length of the ships, and this is the types of ships along that axis. Everything derived from AIS data. Then you hit a button once you have done the model, made the model, and you get a result like this, which tells you that you may expect 0.82 power groundings in this area. One every 2 years, drifting groundings, total groundings of 1.36. Different types of collisions, overtaking, head-on, crossing, merging, bend, and area, which is hitting a small vessel in the area, totaling about 1.89 in this case. And when we compared this result with the historical data, we were astonished. The historical data indicated 1.90. We couldn't believe it. And the groundings, I think, were 0.4 compared to this number here. So that tells us something about the quality of the model, of course. And when we looked at the grounding data, we actually only had grounding data from the Malaysian side. We didn't have anything from the Indonesian side, so we could safely multiply 0.4 with a factor of 2, which then is very, very, very close to this. We were happy. We were expecting something in an order of magnitude, accuracy, and this was mind-blowing. Also, the results can be displayed in a graphical manner, so that you can figure out where are the dangerous sections. So on the polygons, you will see most of them are yellow, but there might be a single one which is more red than the other one. There's an orange one up there. This would then be an area of interest where you would like to take a closer look and understand what's going on there. For the legs, you have different colors indicating collision, different types of collisions on the legs, head-on, overtaking, etc. And here you could have a bend collision, perhaps. So there's the entry to this port here. It seems to be a more dangerous area than many other areas. This scale is relative, so if it's very red, it doesn't necessarily mean that it's very dangerous, but it's just relative to all the others that it is more dangerous. So this magical factor that I was talking about before, causation factor here, which we multiply the candidates with to arrive at number of, or the frequency of incidents. It's a difficult one to select. There have been many studies. This, I guess it was in the 70s that Fuji started some work on this, and there have been many studies and many values, but we have picked a set of values which are kind of an average, and our best guess for these different type of causation factors based on historical studies. And these are the values that we have chosen. We also think that a passenger ship or a fast ferry would be far more cautious than other types of ferries, so we automatically have a fixed factor of 20 that they are better than others, so the causation factor is reduced by a factor of 20 actually for these types of ships. But the analyst that is doing the work is able to adjust these factors and choose factors that he or she might find better suited. So, of course, being who I am, I don't want to disappoint anybody. I have to show you a Bayesian network. This is a Bayesian network which attempts to model the effect of ACE navigation onto the causation factors. We work with three goodness factors: positional awareness, navigator alertness, and traffic situation awareness. And we have a number of factors that influence these, and they in turn influence the grounding and causation factor, or set of factors. So this is a model which hasn't been developed fully, but is under development. A wiki site has been put up with a lot of useful information on IRA. We have a user manual. We have a theory segment telling us something about the algorithms behind. We have a frequently asked question section. And then we have a wish list for future developments. And I invite everybody who have an interest in this to study the wiki and even contribute if you feel